Okay, the final method we have here is Scarlet coin, and judging from the final return statement, um, which recursively calls Scarlet coin on split portions of sorted array. This is a recursive method. So let's start from the base case. We have start and end index. If start equals to n, or n is just like one index next to start, we will check that whether the value at start is equal to x. If it is not, then we will get the middle index. You can verify on your own that this computational formula over here will get you the correct middle index. Just note that start minus n, it will be a negative value, meaning that we are getting the middle index backwards from the n index. Okay, so with the middle index, we again check that whether we have the value x. If that's not the case, then we split the entire sorted array into the left half and the right half. And at each split portion, we check for the if condition. Otherwise, we also get the middle index and check that if the middle index returns x value. If it doesn't return x value, then we further split it into left and right portions. Yeah, and it will go on and on. So in this case, the worst case, which is the condition that we can upper bound on, is that if split portion start does not equal to x, or that like split portion middle does not equal to x, then we will just like keep splitting the split portions into half. Like eventually we will check for all items in the sorted array. This means that the upper bound expressed in big O terms would just be like O of the length of the sorted array, which is omega n as given in the problem itself. Okay, note that the algorithm here greatly resembles binary search. However, in binary search, we narrow down the part of the sorted array to recursively call the function on. Like for example, if you know that x is smaller than start, then I would just like recursively call Scarlet coin on the left portion. Otherwise, like if x is larger than the value at index n, then I will recursively call Scarlet coin on the right portion. So in this case, since like Scarlet coin recursively checks for like the existence of like x at start and middle of each of the split portions, it is not a binary search. Okay, so like just one thing to note. Okay, so for part B, why can we only give like a big O runtime but not a tether runtime? So we know that the rule is that if our function for a big omega, which denotes the lower bound function, equals to our big O function, that is the upper bound function, then we will have a tether function, like on average expression. In our case, let's think about the lower bound. Like for lower bound, that means that we are able to return true if the start index of our sorted array is equals to like x, or that the middle index of our sorted array is x2. So like in both of these cases, it would just take like constant time. However, like we get that our upper bound case is like big O n. Since they clearly don't equal to each other, so we don't have a tether expression in this case. Thank you.